Right, I shall start by proving that the equation of a parabola has the form y equals to x squared. Or perhaps I should say y equals to ax squared plus some constant b. Okay, I shall start with the definition of a parabola. If there is a line and a fixed point, which I call f, and the parabola is a curve such that any point on the curve has the same distance from the fixed point and from the straight line. So this fixed point is called a focus and the straight line is called a directrix. So using this definition, let's put in some coordinates. Let's say that's the x and the y coordinates. Now suppose that the x-axis here is the directrix. Then suppose that the focus is somewhere there. Let's say the y-coordinate of the focus is at f. Okay. Then the curve looks like this. And we can find the equation for this curve using this focus directrix definition. Consider a certain point here, x, y. Now, the distance of this point from the directrix is just y, the y coordinate. And the distance from this point to the focus, we can find using Pythagoras theorem. So this line is supposed to be the same length as this line. Okay, now using Pythagoras theorem, we know that if this point is xy, this point is f, then this distance, I should call that f and p. Fp squared is equal to, I can use the Pythagoras theorem. The horizontal distance is x, so that's x squared, plus the vertical distance from here. If I draw a right angled triangle, the vertical distance is y minus f. So I square that, and this gives fp squared, this distance squared, according to Pythagoras theorem. Now, the fp we know from the definition of a parabola is equal to this vertical distance from the directrix, which in this case is y. So fp squared would be y squared. Now let me expand that. Y squared minus 2fy plus f squared. Now we find that I have y squared on both sides, so they cancel. Let me then bring this over to the other side. I'll get 2fy equals to x squared plus f squared. Finally, making y the subject, we divide both sides by 2f, and we have 1 over 2f times x squared plus f squared over 2f. So now we have the parabola in the more familiar form, containing x squared plus some constants on one side and y on the other side, right, in this form that I tried to prove. So this is how the definition of parabola leads to this familiar form, the x squared form of the equation. Okay, next I want to do a proof for the ellipse. This is a familiar form of an equation for an ellipse. Again, we start from the definition of an ellipse. Now, there are more than one definition for an ellipse. One of them follows the same idea as the directrix focus definition for a parabola. Now, whereas for a parabola, the distance from a point on the curve to the focus must be equal to the distance from that point to this fixed line called directrix. So those two distances must be equal. In the case of an ellipse, this distance must always be the same fraction of this distance. So for example, if this distance is always exactly half of this distance, then the curve would be an ellipse. Now, using this definition, we can actually go through a similar calculation using Pythagoras theorem and so on, and arrive at this form of the equation of the ellipse quite easily. So since that is actually quite easy to do, I shall not do it. I shall do something more difficult, but perhaps more interesting. I shall start with another definition of the ellipse. I shall start with the one that says that an ellipse has two foci. Foci as in the plural for focus. I'll just call it F1 and F2. Then any point on an ellipse, for any point on the ellipse, the sum of distances of that point from the two foci must be a constant. So this means that if I go to another point, say there, then if I add up these two distances, the answer must be the same as for this point. Okay, so no matter where I am on the ellipse. Now you can even imagine putting two nails there, or two pins at this point and this point, and tying a piece of string, a loose piece of string, to those two pins, and then stretching the string out with a pen, and then move the pen around, keeping the string taut all the time. And if you do that with the pen on the paper, you would actually trace out a perfect ellipse, or almost perfect ellipse. So that's a nice way to visualize this definition. Now, using this definition, I shall try and show that we can arrive at this form of the equation. Let me start with the x and y coordinates. I'll sketch the curve for x squared over a squared plus x squared over plus y squared over b squared equals to 1. It would look like an ellipse with the curve crossing the x-axis at A and the y-axis at B. Now it's quite easy to see roughly that the curve has to do this when y is 0. If we set y to 0 there and solve for x, we get A. If we set x to 0 and solve for y, we'll get B for the y. And likewise, we can get these 2 points where it cuts the x and y axis. Okay, and in between, we know that the curve cannot increase to big values of x and y, because the square of x and the square of y added together this way must always be equal to 1. So x can't just increase to very large values. So let's make use of this equation and show that it can be obtained from the definition of the ellipse. I shall start by letting the foci be here and here. So let this coordinate be f and let this be minus f. Okay, now this is what we want to show. So I want to prove this form for an ellipse. Alright, prove that an ellipse has an equation of this form. So, which means that I do not know that this ellipse has this form yet, but I'm just going to take this as make use of the definition of the ellipse. I do know that an ellipse is symmetrical, okay, about two axes. So I'm going to let A be what we would call the semi-major axis, so the longer axis, distance from the center to the curve of the longer axis, and B is the distance from center to the curve along the shorter axis. So since this is an ellipse, and since I have let those 2 points be the foci, then if I consider a point, any point P on the ellipse, then the sum of this line and this line must be a constant no matter where that point is. Now let this distance be C. Now suppose that D is the total length of this. Okay, so let the total length of these two lines be D, so D must always be fixed. Therefore this length must be D of D minus C. Right, and let's say the coordinates of P is x, y. So now I can use Pythagoras theorem to write down the relation between these letters. So for this side C, I have C squared is equal to, between those 2 points, the horizontal distance is x minus f, right, the x there and the f there. I put that in the Pythagoras theorem. Vertical is y, so y squared. So we get this from the Pythagoras theorem for this side. For the other length, D minus C, we can use Pythagoras theorem again to find the distance between this point and that point. So the horizontal distance is x plus f. Vertical is again y. Next, let's find the relation between AB and F. Now suppose that this point is here, where this letter A is. If P comes down here, then the length become the total length become this distance plus this distance. Now if you think about this distance plus this distance, okay, suppose that I take out this part of that distance and put it down here, then I would be going from this point to A and then coming back here. So therefore when P is down here, this length becomes the same as the length going from O to A and back, which is 2A. Right? Since we have said that D is the total distance between of these two lines, we therefore have D equals to 2A. Now, next, suppose that P, this is when this is for P at, I'll call this point A. Now I'll call that point B. So for P at B, for P at B, the distance from here and from here are the same. Okay, so therefore the distance, say from here to here, is D over 2. Right, from B to, say, if I call that point F, this would be BF. It's D over 2, and we can relate this distance to these two distances using Pythagoras theorem again. So therefore this distance squared along here is equal to f squared plus b squared. Okay, so let's not confuse this part. So therefore, since D is equal to 2A, we can substitute this into here. So we have 2A over 2, and that gives A squared equals to B squared plus F squared. Okay. So now we have this, let me call this equation 1, call that equation 2, call that equation 3, and equation 4. We can now start working on these two equations and make use of 1 and 2. Let me start from this equation 3. I have c squared is equal to, so that would be x squared minus 2xf plus f squared plus y squared. Now, If we go back to what we want to prove, this is the form that I want to prove. So if this is true, right, assuming that this is true, then if I substitute this into 3 and 4, I must be able to show that because 3 and 4 gives me the length of these two sides, I must be able to show that substituting this equation into 3 and 4 will give a total of these two sides that is equal to a constant, which is d. So that's what I shall try and do. Now this equation, if I rearrange to make y squared the subject, I'll call that equation 0. So from equation 0, if I make y squared the subject, this is what I'll get. Y equals, I'll bring x squared over a squared to the other side to get 1 minus x squared over a squared. And then I'll bring b squared over, that gives b squared for this. So I can substitute this into the x squared here. So c squared is equal to x squared minus 2xf plus f squared plus y squared, which is that. So this is b squared minus b squared x squared over a squared. That is this. Now let's try and simplify this. You see, f squared plus b squared we already know from equation 2 that it is a squared from there. So this is a squared. Okay. So let me write down some of the other terms. So that would be minus 2fx from there. And those two I could combine to give x squared bracket 1 minus b squared over a squared. Now for 1 minus b squared over a squared, I can make use of this again, because this can be written as a squared minus b squared over a squared minus 2fx plus a squared. And according to this, a squared minus b squared is f squared. Okay, so that's a squared minus b squared, so that's f squared. Therefore c squared is x squared times f squared over a squared minus 2fx plus a squared. Now I can actually factorize this. Put everything under a squared, and that gives f squared x squared minus 2fx 2f a squared times x plus a to the power 4. This is equal to bracket of fx minus a squared squared. Now I can finally find c. Just have to take the square root. Now I have to be careful about this. Fx minus a squared over a when I take the square root. But it can be plus or minus. So should it be plus or should it be minus? Let's go back and look at what c is. Now c is the length of this. And since it's a length, it has to be positive. Going back to here. Now I can't just take the positive sign because I have a minus sign there. So how do I know whether this is positive or negative? Well, now let's look at a, f and x. Look at a, this is a. Now x is the coordinate of a point on the curve, so x must be less than a, unless p is down here. So x must be less than a. And f, this distance is of course less than a. So that means that both f and x are less than a. So fx minus a squared must be negative. To make c positive, therefore I must take the negative answer. So therefore the answer is a squared minus fx over a. Let me write that down as a minus fx over a. That looks simple enough. Now, is it possible that we could actually obtain this without going through so much algebra? Let's have a quick look. Now we have c is equal to a minus f over a times x. We have a look at this picture. This is a. This is c. Now x here would be this horizontal distance. Now f times x over a. Does that have any obvious meaning from this geometry? F times, so that's f, that's x, and that's a. F times x divided by a. It does not seem clear how we could find a simple relation just by looking at the geometry. So never mind, let's just carry on from here. Now what I found is that c is equal to a minus f x over a. Now the next thing we need to do is to obtain the expression for d minus c. So I have basically solved, in a sense, found an expression for c from this and the other relations. Now I want to find a corresponding relation from d minus c. That means for the other length. C is this length, d minus c is that length. I want to find a corresponding expression for this length so that I can add this length to this length and show that the answer is a constant. Now, but for this length, if you look at this expression for this length, the only difference is the sign in f. That means that the f changes sign. So this means that this is all I need to do if I already know what c is. I already know that c is a minus f over a times x. So all I need is to change the sign of f to get d minus c. Therefore, d minus c is a plus f over ax. This is from the equation 4, which is this one, by changing the sign of f. So from equation 4, f becomes minus f. Alright. Compared to equation 3. Okay, that's the idea. So now that we have an expression for those two, so these are the sides of the two. I can add them up, and on the left, of course, I'll get the total, which is d, as I call it. But the question is this a constant? So let's add up the right hand side. You find that this and this cancel, and you're left with 2a, which is a constant. So what we have shown is that if we assume this expression, then the total length of this side and this side must be a constant. Okay, this completes the proof.